Suppose a grammar is in Chomsky normal form. Then a derivative tree of height k must produce a string of length at least k minus 1, but no longer than 2 to the power k minus 2. But the height of a tree is the length of its longest path. So if our Chomsky normal form has n variables, then any sufficiently long path must repeat a variable. This suggests we can find a pumping lemma for context-free grammars. So suppose we have n variables. The longest path in any tree must start with the initial symbol s and end with the terminal symbol. So we need to repeat a variable if we began at the initial node s, passed through n additional nodes, and ended with the terminal symbol. So if the height of the tree is at least 1 plus n plus 1, or n plus 2, then at least one variable must be repeated. Equivalently, if the height is only n plus 1, we might not have a repeated variable. So remember that a derivative tree of height k can produce a string of length up to 2 to the power k minus 1. So if our derivative tree has height n plus 1, then it can produce strings with length up to 2 to the power n minus 1. Consequently, if our grammar produces a string of length greater than 2 to the power n minus 1, it requires a derivative tree of height at least n plus 2, and the derivation will repeat a variable. Note that while we've been using a left derivation, once we have the derivative tree, we don't need to. For example, we might derive a string s produces AB to ACA to ACA, and so on. But the same derivative tree could also be read as the production and this idea is an important component of a pumping lemma for context-free grammars. So suppose a context-free grammar in Chomsky normal form has n variables, and it produces a string gamma of length greater than 2 to the power n minus 1. Then the derivative tree for that string includes some variable twice. Consequently, we could write our derivation, where x, y, z, w, and u are some strings of terminal symbols. And this means there's a derivation of the form variable a leads to waz, which allows us to pump. S produces xay, a produces waz, a again produces waz, and so on, and that allows us to produce arbitrarily long strings in our language. For example, we might have the derivative tree shown, which can be read as having the derivation. So there is a derivation a produces BAB, that's this section of our derivative tree, which we can use to cycle. So this a here, we know there's a derivation that produces another a further down the line. And we can repeat this a produces another derivation, and so on. And this leads to a pumping theorem for context-free grammars. Suppose we have a CFG whose Chomsky normal form has n variables, and let there be a string in the language whose length is greater than 2 to the n minus 1. Then our string is some concatenation of symbols where the length of wz is strictly greater than 0, u is not the empty string, and for any k, we can increase the length of the middle section. Our theorem as stated required that the length of the string be greater than 2n minus 1. This forced our derivative tree to have height at least n plus 2, and since the longest string that can be produced by such a derivative tree has length 2 to the n, we could instead simply require that the length of our string be greater than or equal to 2 to the power n. And note, there could be a lot of strings that fall between length 2 to the power n minus 1 and 2 to the power n, so this is a stricter requirement. So why would we do that? Now, it would still be true that we'd have a cycle of this form, and it's still true that we'll get. However, since the cycle is part of the derivative tree, the length of the path must be less than n plus 2. Which means the length of the pumping portion has to be less than or equal to 2 to the n, and this allows us to state a different version of the theorem. Suppose we have, as before, a context-free grammar in Chomsky normal form with a string whose length is greater than 2 to the power n. Then this string can be rewritten this way, where wz has length greater than 1, u is not the empty set, the central portion can be repeated, and that central bit has length less than or equal to 2n. And we'll make one more modification. Since a context-free grammar has a finite number of variables, the actual number doesn't matter. Consequently, the most useful form of the pumping lemma is let G be a context-free grammar. There's some n, where if gamma in our language has length greater than or equal to n, then gamma can be rewritten this way, where all the usual things apply, and that central portion is strictly less than or equal to n. In other words, there's some string that will cause us to repeat. As with the pumping theorem for regular languages, this theorem is useful for proving that there are languages that are not context-free grammars. We'll take a look at that next.